Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders year 2018, problem number 2. Let m be greater than or equal m, 2, and let it be an integer, and let capital M be a finite monoid, satisfying the following condition: a to the power of m is not equal a for a not equal 1. Of course, by this number 1 I mean the neutral element of this monoid. We wish to show that M is in fact a group. So every element should have its inverse. It's a nice problem. Here are my hints. Yes, so basically here are my hints. First, fix any element A of our monoid and consider the following set: a to the power m minus 1, a to the power 2m minus 1, a to the power 3 times m minus 1, and so on. Since our set M is finite, well, in this sequence we must have a repetition. So a to the power k times m minus 1 must be equal a to the power k plus l times m minus 1 for positive integers k and l. Next, justify by easy induction that for every positive integer q, a to the power k m minus 1 equals a to the power k plus lq m minus 1. And now comes the tricky part and the most crucial part. You should be able to find q and r, positive integers q and r, satisfying the following condition: m times k times m minus 1 plus r should be equal k plus lq times m minus 1 plus r. And if you find these integers q and r, you should multiply on both sides by a to the power of r. And finally, use the assumption that for every element of our monoid, using this contraposition, if b to the power of m equals b, then b equals 1. And that should be it. So give this problem a try, and I will see you in just a minute. Right. So, as I suggested, let a be an element of our monoid, and we consider the following set: a to the power m minus 1, a to the power 2m minus 1, a to the power 3m minus 1, and so on and so on and so on, up to infinity. Now, since m is finite, we can conclude the following, that there are positive integers k and l such that a to the power k m minus 1 equals a to the power k plus l m minus 1. Now, notice the following. If I take this equation, if I take this equality, and if I multiply on both sides by, for example, a to the power lm minus 1, notice what happens. Well, on the left-hand side, I have a to the power k plus l m minus 1, and on the right-hand side, I have a k plus 2l times m minus 1. But notice that this equals a to the power k m minus 1. So in essence, I was able to produce 2 right here. Well, what happens if I multiply once again by this? If I multiply once again, I have a k plus 2l m minus 1 equals a to the power k plus 3 times l m minus 1. But notice again, we have demonstrated that this equals a to the power k m minus 1. And so on. You probably guess what's happening. It's easy induction if you wish to do it inductively, but we see that in fact for any positive integer q, a to the power k m minus 1 equals a to the power k plus l times q times m minus 1. Again, if you do not believe, easy induction to verify that. I am convinced, so I will proceed. Now, crucial part. We will find what exactly? We'll find q and r, positive integers q and r, satisfying that k m minus 1 plus r times m equals k plus l q m minus 1. And to find such numbers, we'll solve this equation for r. How can we do it? Well, notice that we have what exactly? Here we have k m minus 1 times m plus m minus 1 times r. I put this r on the left hand side. It equals k plus l q m minus 1. Notice that m minus 1 cancels, and we are able to find that r equals k plus lq minus km. And remember that k, l, and m are fixed. So for sufficiently large q, we have that r is also a positive integer, because L, K, and M are positive integers. So now we will have the following. I will take my equation, this equation right here. I will take this equation right here, and I will multiply this equation on both sides by a to the power of r, where r satisfies the condition given previously. And notice that if I do it, I have now on the left hand side, I have k m minus 1 plus r, and on the right hand side, we have a k plus lq m minus 1 plus r. And remember that r and q satisfy this condition. The number on the right hand side equals m times this. So we have the following. So now we have the following. A k m minus 1 plus r equals a to the power m k m minus 1 plus r. The number of the right hand side is m times the number of the left hand side. And now, finally, notice that we can write it in the following way. Let's call this part, for the sake of brevity, let's call, I'm running out of letters. Let's call S equals k m minus 1 plus r. Then we have the following. A to the power of s equals a to the power of s to the power of m. And also, by the way, notice that I have multiplied by a to the power of r, and it was legal because r has been chosen to be a positive number. So a to any positive integer makes sense. And now a to the power of s equals a to the power s to the power of m by assumption that for every element b of our monoid, if b to the power of m equals b, then b equals 1, we can safely conclude that a to the power of s equals 1. A to the power of s equals 1 which means that a times a to the power s minus 1 equals 1. Also, note that, of course, all these numbers were positive, so it's greater than or equal 1, so it makes sense to take it to the power s minus 1. Even strictly greater than 1. Alright, so notice that a is invertible, because its inverse is a to the power s minus 1. So every element a of our monoid is invertible, which means that it is a group, i.e. M is a group. And this closes our proof. Very nice problem. A bit complicated at some places, but all in all, it's not the first problem of this type on the Romanian District Mathematical Olympiad. Problems where some algebraic structure is finite and we do this kind of choosing repetitions, it happens from very often on this particular competition. So that is it. So I hope that you've learned something new this time. Thank you very much for watching, and I will see you next time. Goodbye.